I'm Ken Shirriff. I've done a lot of projects with old computers from the 1960s. Computers that used punch cards and were built from transistors, even some vacuum tubes. But the most interesting computer I've restored is the Apollo guidance computer. This computer landed the Apollo spacecraft on the moon in 1969. I'm going to talk about an Apollo guidance computer that was found in a junkyard and how we got it running. So this gray box doesn't look like much, but it's the Apollo guidance computer, or AGC. I'm going to briefly discuss Apollo and then talk more about the guidance computer. Then I'll explain how we restored an AGC to working condition and what we did with it once it was running. Finally, I'll talk about the AGC software and my adventure writing software for it. So first, the Apollo project. In 1961, President John F. Kennedy set the goal of landing a man on the moon before the end of the decade. In 1969, just a few years later, Apollo 11 succeeded and astronauts walked on the moon. Many technologies needed to be developed to make this happen. The Apollo guidance computer is one of them. Now, the Apollo spacecraft has three parts: the lunar module, the command module, and the service module. The lunar module at the top was the spindly part that landed on the moon. Then it left the moon, met up with the command and service modules orbiting the moon. Below it, the cone-shaped command module held the astronauts for most of the time. It returned to Earth and splashed down in the ocean. Finally, the cylindrical service module had the rocket to get from Earth orbit to the moon and back. This is the part that blew up in Apollo 13. I should mention that the Apollo guidance computer wasn't the only computer involved. There were two Apollo guidance computers, one in the command module and one in the lunar module. The lunar module also had an onboard guidance computer for backup. The Saturn V rocket was controlled by the launch vehicle digital computer and the analog flight control computer. These two were mounted in a ring called the instrument unit. There were also many computers on the ground at sites all around the world. Next, the Apollo guidance computer. In the early 1960s, computers had mostly moved out of the vacuum tube era and used transistors, but they were usually very big. This photo shows the IBM 7094 mainframe, like the one NASA used as seen in the movie Hidden Figures. These computers ran in batch mode, reading data off punch cards, storing data on magnetic tape, and printing results on line printers. So now, how do you put a computer in this era onto a spacecraft for real-time navigation? The solution was the Apollo guidance computer. It was the brain of the spacecraft, connected to many parts of the spacecraft. This diagram shows how it was connected to navigation systems, the engines, displays, telemetry, and astronaut controls. Now, the Apollo guidance computer was one of the very first computers to use integrated circuits. By doing this, it made it very small for its time, small enough that it could fit on a spacecraft. Now, a key job of the Apollo guidance computer was tracking the spacecraft's position. It did this using a device called the Inertial Measurement Unit, or IMU. This contained gyroscopes to measure the spacecraft's angle. It had accelerometers to measure the spacecraft's acceleration. And now, by integrating the acceleration, the AGC could get velocity and then the spacecraft's position. So the Apollo guidance computer was doing a lot of trigonometry and calculation to keep track of where the spacecraft was. Now, here's what the AGC looks like when we opened it up. It splits into two trays with modules plugged into each half. These modules held the circuitry for the computer, and underneath, backplane wiring connected the modules together. On the left are the logic modules that implemented the CPU, as well as input-output. The tray on the right holds the memory and the circuitry to support the memory. Now, the most important decision in the Apollo guidance computer was to use integrated circuits. The AGC used two types of integrated circuits. The CPU is built from NOR gate integrated circuits. The photo on the left shows the die of one of the NOR gates. The second type of integrated circuit was the sense amplifier used in the memory circuits. It was packaged in a round metal can. The arrows in the second photo show how these integrated circuits were mounted in a module. Now, I'd like to emphasize just how risky it was to use integrated circuits at the time. Integrated circuits had just been invented 4 years earlier, and now NASA was betting the success of Apollo on these new integrated circuits. But this was the only way they could make the computer small enough. Now, these were very simple integrated circuits. The NOR gate had just 6 transistors and 8 resistors. The amplifier had 6 transistors and 9 resistors. But even though they were simple, the integrated circuits were much more compact and lightweight than using individual components. Now, in the long term, probably the most important impact of the Apollo guidance computer was that it essentially created the IC industry because it was using so many integrated circuits. At one point, the AGC was consuming 60% of all the integrated circuits produced in the United States. This demand turned integrated circuits from expensive curiosities into cheap, reliable components, and basically made what the computer and electronics industry are today. Now, this block diagram shows the architecture of the Apollo guidance computer. At the center, in green, is the arithmetic logic unit, which could add, subtract, multiply, and divide. The CPU had a few registers, which are shown in red. Now, the purple circuitry is input-output, which was very important, communicating with the rest of the spacecraft. The blue boxes on the right are the fixed memory, the ROM, and the erasable memory, the RAM. Finally, the yellow control circuitry controlled the system. Now, it's a basic architecture, but it had a lot of support for input and output. Now, the CPU is pretty strange by modern standards. It had a 15-bit processor. Now, why 15 bits? Well, 14 bits wasn't enough accuracy to get to the moon, and 16 was more than they needed, so they went with 15. And now I'd like to emphasize that there's no microprocessor chip involved here. The CPU is built from thousands of individual NOR gates. The schematic shows how some of these NOR gates were connected to build up latches and other more complex logic. Now, the CPU is fairly slow, even for its time, but it was designed for input-output rather than performance because it needed to have hundreds of connections to parts of the spacecraft. Now, here's one of the logic modules that formed the CPU. You can see the identical NOR gate integrated circuits. Now, this board was very advanced for its time. It had surface mount components with the flat pack integrated circuits and a 7-layer printed circuit board. This was at a time when most things were built with single-layer printed circuit boards and through-hole components. So they were really cutting edge. And at the bottom of the module, you can see the pins that plug into the computer. These are strange pins, which will turn out to be important. One of the most interesting components of the Apollo guidance computer is the core rope modules that held the software. These stored software as wires that were threaded through large magnetic cores, these reddish rings. Now, they literally wove the bits into the module. For a 1, a wire would go through a magnetic core, and for a 0, a wire would go around the core. And then once they'd manufactured the module, the software was now permanent. Now, this seems bizarre now, but it was the best way to get reliable and compact storage at the time. Now, to build the core rope modules, Raytheon hired women with sewing skills and watchmaking skills. They used a hollow needle to thread a thin wire back and forth many, many times through the cores to wire the bits into the module. A semi-automated system positioned the module for each 0 or 1 bit so the wire would go at the right spot. Manufacturing these modules was very time-consuming and expensive, so they didn't want to make a lot of changes to the software. Now, the astronauts communicated with the Apollo guidance computer through a box called the DISCI, the display keyboard. It had a numeric keypad with big buttons that the astronauts could press even with their gloves on. The DISCI had a cutting-edge electroluminescent display to reduce its power consumption. It showed data as 3 lines of digits that had a nice bluish-green color. We didn't have a real DISCI that we could use, so we built a replica DISCI to communicate with the Apollo guidance computer. Now, astronauts would enter a command as a numerical verb and noun, specifying an action and a target for that action. A verb could be anything from displaying a value to enabling an engine. And a noun could be anything from the spacecraft's position to selecting a star for alignment. Next, I'll talk about how we restored the Apollo guidance computer and got it running. Now, people often wonder, how did we get an Apollo guidance computer? Now, before going to the moon, NASA had to test the lunar module on Earth using a very large vacuum chamber. Now, the lunar module in this photo is Lunar Test Article 8, which they used for vacuum chamber testing on the ground. This lunar module is now an exhibit in Houston. However, there's no Apollo guidance computer inside it. Its Apollo guidance computer was sold as scrap. The photo shows the receipt for the scrapped Apollo guidance computer, showing that it was originally $275,000, but they no longer needed it. And that brings us to Jimmy Locke. He was visiting a scrapyard in the 1970s and he bought 2 tons of discarded NASA junk. A few years later, he noticed that there was an Apollo guidance computer in there with the rocket engines and so forth. He decided that it'd be cool to get the Apollo guidance computer working for the 50th anniversary of the moon landing. So he talked to various people about getting it restored. We ended up forming a team to restore Jimmy's scrapyard Apollo guidance computer. Mike Stewart on the left is an expert in the Apollo guidance computer who had been studying it for years. Mark is a computer collector and restorer, well known on YouTube as Curious Mark. Carl restores old IBM computers. So we got together. This photo shows Mike and Mark when we were debugging the Apollo guidance computer in a hotel room in Houston. The Apollo guidance computer is on the left with a bunch of wires attached, and we have a logic analyzer on the right. Our first challenge was how to connect to the Apollo guidance computer. It has rows of connectors on the front, 2 connectors that were connected to the spacecraft, and a covered test connector for debugging. Unfortunately, the connectors used special aerospace pins that were called mini-WASP. These pins were briefly popular in the 1960s and then completely disappeared. We couldn't find anything compatible. Fortunately, the connector company Samtec built us custom gold-plated pins using the original NASA blueprints. So once we had these pins, I'm inserting them into a connector in the photo, and we hooked that connector up to the Apollo guidance computer. Once we had pins, we built a bunch of peripherals to hook up to the Apollo guidance computer. Mike designed an FPGA-based interface that plugged into the test connector on the Apollo guidance computer and gave us full control. In the first photo, you can see it plugged into the AGC. We also built a core rope simulator, a plug board for the I/O connections, and the replica disk E. We started by testing the complex power supplies. The power supply converts the spacecraft's 28 volts into lower voltages for the computer. Your cell phone charger uses a switching power supply, but back in the 1960s, switching power supplies were rare and complex. They were used in aerospace because they were compact and efficient. We carefully tested the components, no bad capacitors or anything else. Then we powered up the power supply and it worked perfectly. The voltages were exactly right after 50 years. NASA spent a lot of money on highly tested aerospace grade components and it paid off. The power supplies and the analog modules are built with something called cordwood construction. The components are mounted perpendicularly and wires are welded to the ends of the components, so there's no printed circuit board. Cordwood construction was often used in aerospace because it was compact. The module would be encased in epoxy for flight to protect from vibrations, but our module was used for ground testing, so they didn't use epoxy. The computer's RAM, though, caused us a lot of trouble. It only had 2K of memory built from tiny magnetic cores threaded on a grid of wires. Magnetic core memory was very common in the 1960s before semiconductor memory came along. Each tiny magnetic core stores 1 bit. It's magnetized one direction for a 0 and the other direction for a 1. The wires through the cores flip the magnetization to read and write the core. Unfortunately, the memory module had a broken wire. The memory held 15 bits plus parity, but 1 bit didn't work. To make things worse, the entire module was encased in epoxy, so we couldn't see inside. We took detailed x-rays of the module, which you can see in this photo, but we couldn't find the broken wire. This was a big problem for us since the computer wouldn't work without memory. Fortunately, Mike came up with a clever fix. He rewired part of the AGC to disable parity checking, and then he used the working parity bit to replace the bad data bit. Now, this wouldn't be reliable enough to fly to the moon without parity, but it fixed the problem for us. Here's a photo showing us debugging a timing problem on the AGC. You can see the purple wire wrap wire that forms the computer's backplane. We found another problem in the current switch module. This module generates high current pulses to magnetize the cores in the core memory. Some of the diodes had gone bad. To replace the failed components, we had to carefully chip away the solid epoxy without damaging any of the wires or components. It was like digging through rock for fossils. We replaced some diodes in the transistor and got the module working. So eventually we got the whole computer working. Here's a photo of us in the newspaper with the Apollo guidance computer. That's Mike, Carl, me, and Mark in the photo. And the Wall Street Journal also wrote about us. Now that we had to fix the Apollo guidance computer, what could we do with it? Well, we went to Florida and visited Eldon Hall, who was the inventor of the Apollo guidance computer and had created it in the 1960s. He was very happy and surprised to see the computer running again. We could also run the original software from the lunar landings and simulate a landing on the moon. We hooked the Apollo guidance computer up to a PC that simulated the spacecraft controls. Someone had written a simulator. So now we could run the original Apollo 11 software on the real Apollo guidance computer and control it through a PC. Mike did a whole bunch of simulated moon landings successfully, but the rest of us would crash. It's very complicated to flip all the right switches at the right time. So we also used the AGC to preserve some of the original software. Some museums and collectors had core rope modules with software from various Apollo missions, but they didn't have any way to read the software. But we could plug the core rope modules into the AGC and then read out the data to a laptop. So this software is now archived online for historical research. So now I'll talk a bit about the software. I wanted to write some software for the Apollo guidance computer. The original AGC software was very complex. This famous photo shows Margaret Hamilton, director of CSM programming, standing in front of a stack of AGC software printouts. In total, the AGC software took 1,400 person years to develop, programmed in assembly language. Now, if you've written software, you can probably relate to the quote. The effort needed for the software turned out to be grossly underestimated. The Apollo guidance computer had a complex operating system called the executive. It supported 8 jobs running at once. Jobs ran sequentially on the CPU based on their priority. A wait list kept track of real-time tasks so they could be executed at the right time. Finally, a checkpoint restart feature saved important information so the computer could rapidly restart in case of a fault. This was very important during the moon landing because a radar problem overloaded the system. This caused the famous 1201 and 1202 program alarms that could have aborted the moon landing. But because of the checkpoint restart design, the computer restarted multiple times without interrupting the landing. The AGC software also included an interpreted virtual machine, very advanced for the time. This made it much easier to write the navigation code. It was still like assembly language, but slightly better because it had instructions for matrix operations and trigonometry. Some of the interpreter code is shown on the right. This code computes the positions of the Earth, Moon, and Sun. Now, the mission software itself was also very complex. The lunar module and command module had completely separate software programmed into the core rope modules. On the lunar module, programs had tasks such as realigning the inertial measurement unit, landing on the moon, and getting back to the command module. The command module had programs to handle the launch, getting to the moon, and then getting back to Earth. Now, how did they develop software back then? This Honeywell 1800 mainframe was the AGC programmer's equivalent of GitHub. Programmers would submit changes on punch cards, then the mainframe would integrate the changes onto magnetic tape to keep a master copy of the software while tracking who made each change. The resulting software was assembled, and then it would be manufactured into a core rope module when it was ready. To debug the AGC software, they used a refrigerator-sized debugger that they called the monitor. Now, this worked kind of like a modern debugger. You could set breakpoints, single step through your code, examine memory, and so forth. Now, fortunately for me, when I wrote an AGC program, it was much easier. A group built a modern integrated development environment called Code Blocks, so I could write and debug an AGC program on my laptop and then download it to the real Apollo guidance computer. You can also use this development environment to write programs and run them on a simulated AGC if you don't have a real one available. Writing AGC software is still difficult, though. The instruction set for the AGC is very strange. Because the instruction size and memory were limited, they used a bunch of hacks. For instance, one strange instruction in the AGC is count, compare, and skip, which they used for loops. It includes a 4-way branch, depending on if the result is positive, negative, positive 0, or negative 0. Yes, the AGC had both positive and negative zeros. Now, another weird instruction is transfer accumulator to storage. That sounds pretty straightforward. But if a previous arithmetic instruction had overflowed, this instruction would turn into a jump. So kind of strange. Finally, the AGC doesn't have instructions to shift a number. Instead, it has these magic memory locations. If you put a number into one of these locations, it will be shifted when you take it out. So now what kind of program did I want to write for the AGC to demonstrate its performance? I wanted something that was kind of pointless and anachronistic. So I chose Bitcoin mining. Now, the Apollo guidance computer is a really bad choice for Bitcoin mining. The memory is very small, the 15-bit words are an inconvenient size, and the instruction set doesn't have the bit operations that would be convenient. But I was able to get it working. Some of the code you can see on the right. Now, modern Bitcoin hardware performs billions of hashes per second. The Apollo guidance computer, on the other hand, takes over 5 seconds for just one hash. Now, the result is that it would take 1 million times the age of the universe to successfully mine Bitcoin. So mining Bitcoin on the Apollo guidance computer is not going to be very profitable. Now, this video shows the Bitcoin mining running on the Apollo guidance computer. So first, I enter verb 65. This verb I programmed to do Bitcoin mining. Now the AGC thinks and calculates for a few seconds, and then there's the result. It displays the hash, starts with a bunch of zeros, and then you can see the remainder of the hash shown in octal. So there you have it. The Apollo guidance computer from the moon to Bitcoin. Thank you.
Bienvenidos nuevamente al Track Nerd. Y aquí tenemos a Ken Shirriff que nos va a contestar algunas preguntas después de su charla. Hi Ken, how are you?
Hello, good to be here.
Very glad to have you here. So I'm going to ask you a couple of questions from the audience, and then you can answer. So
okay.
How much did NASA get from the AGC as scrap? Do you know?
So I think they sold it for the scrap metal value, the cost of the gold inside. So they probably got like $1 a pound. So they really wouldn't have gotten much money from it, but they had a lot of stuff to dispose of after the Apollo program ended.
Wow, that's really crazy. So there are a lot of old machine emulators online. How many of those were former space computers?
So the virtual AGC project has built an emulator for the Apollo guidance computer and for the LVDC, and I believe for the onboard guidance system. So there's a few space computers emulated. The space shuttle computer, I haven't seen any emulator for that. But people are always ready more emulators, so I'm hoping to see more space computers in the future.
People love to emulate stuff.
Yeah.
So, web source code is open source. Apollo had any software or just sort gates? How about the space shuttle?
So the source code for Apollo is been scanned. It's available online. There's people who are collecting all the different versions from all the different launches of the Apollo software. I haven't seen any space shuttle software. I think that is still being kept private.
That's too bad. It would be interesting, right?
Yeah, I have a friend with a space shuttle computer, so I opened that up and took a look, but we haven't got it running yet. And it'd be nice to have some software for it if we ever do.
Hopefully soon. So how is the fault tolerance system of the AGC? Is it 2 CPUs? Is there anything else that we can...
So there's, strangely enough, there's really no fault tolerance in the AGC. They just counted it on it being reliable enough for the mission. On the Space Shuttle booster, the LVDC, that computer had 3 copies of everything.
En Telecom potenciamos
3 copies, and 2 out of 3 would win. So that had reliability built in. But the AGC, if something went wrong, they would just probably have to come home. But fortunately, it worked fine for all the missions.
Wow, that's amazing. So what is the impact of the Apollo guidance computer on the computer history?
Well, as I mentioned, I think their support for integrated circuits was the biggest impact. They were buying integrated circuits by the thousands at a time when integrated circuits were like $100 each. So this really built up the computer IC industry. NASA was demanding a lot of reliability. So they did a lot of work to figure out what was going wrong with integrated circuits and make them reliable. So you can really thank the AGC for the cheap, reliable integrated circuits you can get now that are a part of every computer.
That's amazing. So is there something that you learned from just restoring the AGC, sorry?
Well, one thing I learned is just how much computer technology has improved since the time of Apollo. Our computers are so much faster, memories are much, much larger. So the technology has just grown by leaps and bounds. But the other side of that is that the people back then, they were really smart. They were solving hard problems. They could do amazing things with the computers they had available. So looking back at this old technology, I'm always impressed at just how smart the people who built these old systems were, how they dealt with the problems they had. And so we really have to look up to them.
That's amazing. So what Apollo space hardware are you looking for next?
Well, right now we're working on the communication system. We have collectors who've loaned us the radio communication, and we're trying to hook that up. We're able to transmit radio signals from one end of a table to another. So it's not going to the moon, but we are starting to get the communication hardware to work.
That's great. So is there a place where you can kind of guide us and tell us where to find some documentation on this area? I know it's pretty specific, but maybe you have something in mind. So
there's a website called Virtual AGC, where they are doing a lot of the analysis of the Apollo guidance computer, collecting the software and documenting it in detail. And I can put that link in the chat. So I'll do that in a moment.
That's great. Thank you so much. So do you have a social network that you can follow, that we can follow you and kind of follow what you're doing next?
So Twitter is probably the best place to follow me. Ken Shirriff is my handle on Twitter.
Sounds good. Are you going to send a talk to the next Nerdiarla?
Maybe. We'll see what happens. Thanks for inviting me.
No problem. Thank you so much for submitting your talk and having a Q&A with us. And hopefully we'll see you next time.
All right. Well, thanks to everybody who is listening.
Thank you so much. Y vamos a una tanda y ya volvemos.
En Telecom potenciamos tu mundo con